Jai Hind, my dear students. Today we are going to start the new unit, Unit 2 with lecture 1, and the topic is concurrency. So, concurrency plays a very important role when working together. Now, there is very important thing that we must understand that working together, we usually have a chaotic situation. So, I would like to address this topic concurrency with a connotation chaos of concurrency. So, what we will learn today are some important terms like race condition, critical section and synchronization when we are talking about process. Previously, students, we have covered with respect to the operating system concept of process and its states, scheduling, various scheduling approach like priority, and we have also of course discussed the deadlock and the banker's algorithm in context of operating system for the process and its states. Now, moving ahead, we must understand difference between program and the process, and moreover we should understand the hardware also. And to make it understandable, I am using some analogy to make it more relatable. So, program is like an inert file. It is having inertness, okay, and the process is like a living thing, or it is having soul. Similarly, this process will execute on hardware, and it requires certain internal energy. So, program cannot execute, it can execute when it is converted into the process, and the process itself cannot execute unless it is running on hardware. So, if you see what we call as a program, like we may call it as a file which is having nothing, a lifeless thing, and it is a code and cannot compute anything by itself, okay. It does not have any CPU, it does not have any RAM associated allocated to it. So, we are having just a book on the bookshelf, okay. So, in operating system term, it is a passive entity or a static file. We cannot work on that, we can work only when that program is converted into process. So, a process is basically having certain soul like thing, it is living, okay. So, program loaded into RAM plus it is executing is called as process. And certainly when the process comes into life, it is having some identity, like we have names, okay. So, it has names, okay. So, I can understand recognize each process by its name, and we have various states where we are currently now. So, there is a program counter, various registers in the memory. So, when the program is converted into a process, it gets name, okay, and it has multiple things like a state, program counter, registers in the memory. So, it has a life cycle, like it is a newborn, then ready, running, waiting and terminated, okay. And the same code create can be multiple process also for next process also, and it is basically active activity and dynamic in terms of operating system. Now, we have created the process is having certain activity, but this activity is going to be executed on the hardware part. So, the force behind execution is the hardware. So, what are the main hardware? CPU, the RAM, the bus and the IO devices that are making it to execute. So, every process must connect to hardware to execute, and certainly the hardware is something pure and it is complete, and it is basically absolute, or they are called as supreme resources, means that we cannot go beyond hardware, okay. Hardware is my limit, so that's why it is complete and absolute. So, process that we regarded as soul cannot act without the hardware, or we can take an analogy that is Paramatma. Fine. So shared by all process simultaneous. So everybody, that is every process is sharing this hardware. So this hardware is common to all. Okay, everywhere, or you can say it is used by process, every process. Now moving ahead, if you see the stack of this user interaction with the actual hardware, so we can see here the user or process, okay, the soul send request via system call to the kernel, which has rules of some operating system environment. Okay, so here we validate and it route to the hardware. Finally, at the bottom there is the RAM or IO system physical resources, where we store something or handles input output system. Through bus system, we communicate finally to the all the components, and at the bottom there where this will execute, the process will execute user process that will actually work on the CPU. Okay, so finally it executes all the instruction. So process can only act through the hardware, they are inseparable. Process and hardware are working together in hand, we can call it, they are inseparable. Now moving ahead, if we see an analogy of some population of India, so we our world, so there are almost 700 crore people working together or living together in this world. So so in particular case, 140 crore people running on in Indian subcontinent, each person has a unique considered process, considered as a unique process, has own identity, needs something and has some memory, and it has certain goals. So the processes are created, 140 crore processes are created, okay, and they are on the earth, particularly in Indian subcontinent. Okay, so they are using the Indian subcontinent's hardware. So roads, hospitals, banks, okay, power are the things that they are using. So in terms of hardware, it is called as CPU, RAM, disk or IO. So only one subcontinent for all 140 crore people. So this hardware is for 140 crore processes. So how do these 140 crore people share the same roads, hospitals, banks without crashing into each other? So that is a very important question, that is the pertinent philosophy behind the topic, the chaos of concurrency. Okay, so if we see how these work, so there must be some rule for running these 144 crore process concurrently on the particular hardware, and the rule comes here that it should be helping in synchronization. Like say for example, we can just think about this. We have some rule mechanism like traffic signals, we can use token or queue system, okay, we can use booking system, we can use some rules in bank account, okay. So these are something that is the rule system or synchronization mechanism that is needed to utilize this particular hardware or common resource, okay. So without rule there will be a race condition or chaos. So basically if you see the concurrency problem, it is nothing but understanding the rule. If you know the rule, concurrency is there. If you do not know the rule, there will be condition of chaos. So without rule there is a condition of chaos, and if there is a rule there is synchronization or order, okay. So the simple chaos is just opposite to order. If there is order, there is a no chaos. If there is a chaos, it means certainly there is a non-ordering within the processes. So moving ahead, formally concurrency means execution of multiple processes overlapping in time period and does not require multiple cores. Like there, here you can see situation, the concurrency comes only when we have a single core like one CPU. But parallelism, while in the case where you have multiple core, we are not talking about concurrency. Concurrency is only for this particular case where only one CPU is there. Okay. So, what is happening? CPU is one and there are two processes. So, there is one resource here as a CPU and P1 after P2, then P1 after P2 and so on. They are working concurrently. So, execution of multiple processes overlapping time periods. Okay, and it does work on a single core. Okay. So, how this happen? There is a rapid alteration between P1 and P2 and this is called as context switches. So, rapid switching creates an illusion of simultaneous execution to the user. So, this is so much fast that the end user who is using the system, but the system is running concurrent process, feel that multiple processes are running together, but inherently they are working one and after another. Now, this particular situation has one important issue that is called as race condition that can happen here when context switch mid update or there is a corruption of data. Like P1 is switched to P2, okay, and in that process that is called as context switch mid update, means between process 1 and process 2 there is a midpoint or some gap. In that gap, if some update happens in that midpoint while there is a context switch, so certainly we are not aware about that data, what has been changed. So, certainly if there is a change in between, we are having some data being corrupted that I don't know or it is not in my knowledge. So, certainly if you are switching a context and there is some alteration of data, can you rely it? No, we cannot rely it, and that condition is called as race condition, and that another is updating without your knowledge or consent, or you are not well aware of that change. So, basically you are getting corrupted data, or you can say you are not having a coherent viewpoint, fine. While in the case of parallelism, we have two separate hardwares, core 1 and core 2, and they are running continuously on two different cores, and they are, this is called as simultaneous, or they are running together. So, true simultaneous execution on different core, and it does not need any synchronization until unless there is one issue that is called as shared data. Now, the student, you must understand that here the bottleneck is shared data and here the bottleneck is the CPU. So, basically here the hardware is a common point and shared data software is the share point. P1 process 1 and process 2 is running on core 1 and core 2, but they are having a common data, that is a software part that is being shared. So, it may have some concurrency issue. While here the hardware part is common, they are time shared, but hardware part is common. So, there is concurrency issue. So, concurrency issue occurs in hardware as well as when you have some shared data between process and two. So, like see this example, race condition example, when race condition happens and what happens. So, say for example, a variable named count is equals to 5 and process 1 is also working on that and process 2 is working on that. So, if you see the this diagram, the initial value is set to count, that is the register is set to the value of count, and there happens a context switch, fine, there is a gap, and thus register 1 is appended with some value or some arithmetic operation is been done. Now, it is 6, okay, and the count value is now updated from the so ultimately the count is 6 using the process 6. Now, if you see here in the process 2, okay, it is waiting and then it is reading the initial value of count, okay, as it was 5. but it has updated the count value is stored in register 2. Here it is in register 1, and it has added its value by 1. Okay, so it is 6 now. So this is again 6. Now, if they are happening separately, okay, fine, answer is fine, but they are working together. Fine, because we are dependent on each other, race condition. Okay, so if we see this execution process 1 and process 2, if this has happened first and it is happening second, so certainly the count value will have updated to 6. Okay, so here it is basically 6. So it is now updated to 7, and finally the count is updated to 7. So if you see, the expected outcome should be 7, but it is happening to be 6. Okay, because one increment is lost or data is corrupted because there is no concurrency in between the process 1 and process 2. So if you see with another example that you can see with the amount withdrawal from a bank. Okay, so we can also see and relate here only. There is a bank, ATM A Mumbai withdraws 100 rupees, ATM B Delhi withdraws 100 at the same record from the same bank. Okay, so expected correct order is like this. Read ATM A 150. Okay, ATM A deducts 100, so it writes back to 50. ATM B reads it is 50. ATM B says insufficient funds. Final balance is 50. ATM dispenses A. ATM A dispenses the cash. Fine. Because before B gives instruction to withdraw 100, it has already checked that amount is 50. Okay, so that is fine, green path. But in reality, the race condition is looks like this. Okay, this looks like this. ATM A reads 150, ATM B reads 150 before ATM A updates, and ATM A writes 50. Okay, now ATM B writes again 50, that is overwrites A. The final balance is 50. So both dispensed cash, bank lost 100. Basically, it is lost. Fine. Both are giving 100, but ultimately bank has 50. So they have given 200, and we have 150 initially. You have given 200. Fine. So and remaining is 50. So 50 plus 200, 250. Is 250 equivalent to 150? No, it is not. So this is inconsistency due because of synchronization or because of this simultaneous execution on the shared data. Now moving ahead, can we solve this problem? Yes, we will learn this later on in more detail for each and every technique, but we should understand this. Yes, if we see that some portion of the code can be regarded as a critical section, or basically it is a solution structure. So code that assesses shared data, only one process allowed inside that time. So that problem can be solved. So like we can see, this happens in most of the time when we do go for the railway station. We get hospital booking system. When we are using printer or we are going for ATM withdrawal, same thing must happen as the process has some critical data, and that should be bound and not allowed by other process at that time. So we define an entry section, request permission to acquire the log. Okay, then we go inside a critical section, read part. So only one process can use this. Then we exit and then we release log, and the reminder section, normal code will be working without non-shared variable. And this is fundamentally required in all these applications. Okay, and because in railway registration, multiple users are working together, and hospital booking, multiple users are working together. On the shared printer, multiple print requests are coming, and also the ATM is being withdrawal from many places from the same account. So, three things that must be ensured to have a valid solution: mutual exclusion, progress, and bounded waiting. Okay. So, if we see these three things, like mutual exclusion, safety property it is called as, progress means liveness property, and bounded means fairness property. So, basically three important aspects: safety, liveness, and the fairness, that must be preserved. So, we can understand with the analogy, like a bathroom lock, only one person inside, others wait outside. Obvious, not quite difficult to understand. It is a safety issue. Okay. Consider liveness. Okay. Example, empty shop. Okay. Waiting customer must be served. Okay. A guard cannot block for no reason. If the shop does not have any existing customer, no one is waiting, so otherwise why should other be waiting? So, waiting customer must be served. A guard cannot block, no reason. Okay. So, it will be always possible to serve it. There is no waiting time. Okay. Similarly, analogy of bounded waiting, like token queue. Your number will be called within a predictable number of tokens. Okay. If this happens, we can have this valid solution for the problem of critical sections. Okay. For shared variable. Fine. Now, if we see, there are important thing that must be understood. Violation: two process update the balance simultaneously. The race condition happens. Strict alteration: CS may be empty and the process 0 wants in, but P1 is the reminder must set the turn first. Okay, so there should be a strict alteration between P0 and P1. Similarly, mutual exclusion is enforced, but other process cut the queue forever. That is starvation. Okay, if it is being bounded waiting is not being held, okay, violation happens. There is a very big problem, starvation. So, starvation may happen if the bounded wait is not there. Okay. Likewise, all these things must be ensured. So, going more in detail, there are three types of solution has been proposed: Peterson solution, semaphore solution, and test and set solution proposed, and they have various implications and the requirement with the application. Okay, so basically, if you see, the Peterson solution is a software based solution, pure software solution, while semaphore uses a integer variable with weight and signal, while test and set is a atomic read modify solution, right in one hardware step. So, basically this is a hardware instruction, this is OS level implementation, and this is a software implementation. So, at the top level we can use Peterson solution. Okay, and they have certain advantage and disadvantage. Certainly, if it is the top most level, the software implementation, it will be having some issue of slowness because of moving down to the hardware level. And finally, this is the faster one because it handle at the hardware. So, this is impractical in modern multiprocessor system. Okay, because it will impact the overall speed. This is good when one resource is fine, but when there is multiple resources, it's very difficult. And Linux kernel uses complex exchange of instruction to use this. Okay, so the hardware runs every process. Okay, hardware runs every process, but every process need to follow the rule. Every process need to follow the rule to live together, and that rule is called as synchronization. Very simple. if you see student, when we are working together, multiple person together, the persons cannot have their own rules. They cannot have their different dharmas, okay, or their different rules. We cannot live together. We can live in the rules that is true, that is based on facts, and that's only it will cause the synchronization among the processes or the persons. Thank you for listening this important introductory lecture for the topic concurrency. And the concurrency is a very important topic in operating system, and nowadays it plays a very important role, especially to the programmer when you are working on a multi-process and multi-core systems. Thank you and Jai.